So we want to be thinking about the efficiency of every algorithm we write, but one time when efficiency becomes very important typically is when you're dealing with collections of objects. Because again, if you have a data set, a collection of things, and you have an algorithm that's going to process that collection somehow, you need to think about how that algorithm is going to, the execution time is going to grow as your problem size grows. So in particular, we want to think about how implementing collections and abstract data types with arrays compares to implementing with nodes. So we want to be thinking about the efficiency of array-based code versus node-based code. And you have to really understand your problem and your solution in order to figure out what the right implementation is. So I have here, this is for arrays and link to nodes, and this is a link to nodes with a head pointer only. And these are some different algorithms that you might implement on a collection of objects that's either held in an array or held in a collection of linked nodes. What I want you to do is pause the video, write down the order of growth for all of these without looking at anything. Just think about it. Think about how it depends on the size of the data set. So pause this video and write down all of those, and then when you come back, we'll go through them. All right, so let's talk about these. So we've got traversal. So that's anything that goes over your data set, whether you're saying, how often does an element appear? Does this element appear at all? Is it contained? If I want to fill up my list, if I want to print out everything in my list, anything like that, that's going to be O of n, whether you implement with array or with linked nodes, right? If you have to traverse through the whole list, it's going to be O of n. Okay. Now, if you try to retrieve an element at a specific position, so say, give me the 10th item in the list, with an array, that's O of 1, constant time, right? With an array, we can just get it. With linked nodes, it's order n. We have to traverse through the first n nodes, current.next.next.next.next 10 times to find the 10th item. And as our problem set grows, let's say, for example, instead of finding the 10th item, we wanted to find the third from the last item. Well, the number of things nodes we'll have to iterate through is going to grow at the same rate as our problem size grows. If our list grows from 10 to 20, the number of things we have to iterate through is going to increase from 7 to 17. So it increases at the same rate, order n. When we think about insertion for arrays, if we insert at the beginning of an array or in the middle of an array, that's going to be order n. And it is that because of all the shifting. If you need to put something in the beginning of the array, you have to shift everything else down. And anytime you're, applying something to every item in the array, that's going to be order n. If you insert in the end, it's constant time. Now, for linked nodes, it's not the same, right? If we insert at the beginning, that's order 1. That's constant time. All we do is we update those first node or head node pointers and references. If we insert at the end or in the middle, that's going to be linear O of n. Because again, to do those insertions, we have to traverse through to the middle position or traverse through to the ending position in order to insert. Now, deletion is similar. For arrays, if we delete from the beginning or the middle, it's going to be O of n, and that's because we have to do that shifting to cover up the gap. So the shifting is always going to grow at the same rate as the array size grows, right? If we have an array of size 100, we want to delete something from the middle, let's say we have to shift 50 elements over. If we double our array size to 200, and we want to delete something from the middle, we'll now have to shift over 100 elements. So our problem size is growing at the same rate. Deleting from the end is just, again, order 1. And similar for linked nodes, similar to addition, deleting from the beginning is very easy. It's constant time. Deleting from the end or the middle is order n, because again, we have to traverse through to the spot that we want to delete from. Now, how would this change if we had linked nodes with a head and a tail? So this should say head and tail. Which of these efficiencies would change? I'm not going to answer that question. I'm going to leave it up to you to think about and think really specifically about how you would do your insertions and deletions at the end if you had a tail pointer. How would they change? And what would that improve the efficiency of? What wouldn't change? Okay, so that's in general array implementations and linked implementations. But now let's look at our specific classes and interfaces we've been using. So if we think about bag interface, we have 2 implementations, array bag and linked bag. And here's all our methods. We've got the 1 add, we've got the 2 removes, clear, oops, actually, no, yeah, that's it. Sorry, I thought I missed something. Get frequency of, contains, to array, get current size, and is empty. So again, pause this video, fill out this chart, thinking about how these methods work, and see if you can come up with the order of growth for all of them. And here they are. So for array bag, add and remove, the first two the add and the first remove are constant time. Removing a specific element is n, order n, because of course you have to traverse through the array to see if that element exists. Clearing out is order n. Actually, I think this is, yeah, that's order n, right? Because we go through and I believe they null out, the implementation is you null out each item in the array. Get frequency of is going to be order n because you have to look through the whole array. Contains, same thing. To array, same thing. Get current size and is empty are constant time. Now for linked bag, it's very similar. Adding and removing is order 1. Removing a certain element is order n. Clearing, get frequency of, and contains, and to array is order n, and get current size and is empty is order 1. This is very unusual that the order of growth for an array-based and a linked node-based implementation would be the same. This highlights how simplistic the bag interface is. Bags are very simple, right? They don't have any order. They don't give us a lot of ability to manipulate things. We can't just obtain an element from the bag without removing it. So they're a very simple data structure, and that's why the orders of growth between arrays and linked bags are the same. This will usually not be the case. Usually there are differences between an array-based implementation and a linked node-based implementation, as we saw with the general chart I put up at the beginning of this video. So let's think about list interface. So again, take a moment, pause the video, think about the orders of growth for the A-list methods and for the L-list methods. Okay, so here for A-list, we have the two adds. One is adding to the end and one is adding at a certain position. Adding to the end is just order 1. Adding at a certain position is going to be linear, O of n. Removing from a certain position is going to be order n. This again highlights the worst case aspect of big O, because of course if we're removing the very last element, we know that's going to be constant time, but we have to take the worst case. It could be removing the very first, right? So that's what we're reporting on, is that worst case. Get entry again is constant. Replace is constant. Contains is order n. To array order n. Get length is empty and clear. Now for L-list, some of these are similar, but a lot of them are different, right? So adding and removing, all three of those are order n. This is a big difference here. Adding to the end of an A-list object is constant time, and adding to the end of an L-list object is order n. So that's a big, big difference. Okay. The other big difference here is get entry. So getting a specific entry at a specific position of A-list is constant, L-list linear time. Okay. Similar for replace, and contains is order n for both. So the add and the get are the big differences here. And again, the reason for that is because with an array-based implementation, we can always jump directly to an element. And with a linked node implementation, we can't do that. And remember too that L-list only has a head pointer. It only has a first node pointer. We don't have a tail pointer. Okay, and sorry, I did want to check. There is one typo on here. Clear is order n in L-list. I thought something didn't look right here. So if you look at the clear method in L-list, is O of n in A-list. It's constant time in L-list. So in the A-list clear method, you actually traverse through the whole array and null everything out. For the L-list, you just update first node and number of entries. So this one is correct. This one should be order n, and I'll update that in the slides. Sorry about that. But again, think about these differences between the array-based and the linked list-based, the linked node-based, and your important distinctions are going to come in with the adds and with the gets. So when we think about list implementation, so these are classes that implement the Java standard library list interface. We've got two classes that we use, array list and linked list. Again, these are the classes you're going to use in the real world, right? You're not going to get out there and use list interface and A list and L list. You're going to use array list, linked list, and list. So these are the really important ones to know. And you can look at the API pages to get some more information about the efficiencies. But here's just a little summary. In terms of direct access, that's the get method. It is order 1 with array list, just like with A list, and it's order n with linked list. So if you want to get an element at a certain position and you're using a linked list, that is not a quick task. It's linear time to just get an item off the list at a given position. Okay. Now adding and removing from the beginning, order n with an array list, order 1 with a linked list. Adding or removing from the middle, order n with an array list, order n with a linked list, but you can use an iterator, which will improve this to order 1. I'm not going to talk about that here, but if you want to look into that a little bit, hopefully you'll see what I mean and how that works. You can look up iterators a little bit and you can see how that efficiency is made. Adding or removing from the end is O of 1 and O of 1. With an array list and with a linked list, so constant time. Think about what it is about linked list that makes this constant time versus our LList class removing from the end is linear time. So what is the difference between linked list and LList? There are two really important differences that make one of them run in that algorithm in linear time and one run in constant time. So these are the real ones you want to think about because these are the real classes that you'll use in the real world. But hopefully seeing the behind the scenes code for A-list and L-list helps you understand why some of these actions are linear versus constant.